Listo. Listo.
Perfecto. Okay. Okay, so hello, good afternoon, everyone. And thank you for being here for this series of seminars of Alma, Asociación Latinoamericana de Magnetismo. My name is Dr. Flavia Gomez Albarracin, and I'm going to make a brief introduction about Alma. So Alma is a Latin American Magnetism Association. Our goal is to promote and encourage collaboration between the different Latin American countries and Latin American scientists in other parts of the world, and to reinforce and create new bonds between groups with a rich exchange of research and human resources. If you're interested, you can join us at this address. You can write us at this address, almamagnetism@gmail.com. And there is a very easy to find Facebook group you can also join. So here, we are here to present our webinar, very interesting about Spintronics. Dr. Adriana Figueroa, who works in Barcelona, Spain, is going to give us this webinar. As you can see, this is a Zoom event, and it is also live streamed at YouTube. This webinar is a part of a series of events organized by Alma, the Asociación Latinoamericana de Magnetismo. And this is a number of events are going on. The webinars have been going on for a while. But before that, let me talk to you a bit more about Alma. There are different nodes in Latin America. Right now, we have people from 6 different countries: Mexico, Colombia, Peru, Chile, Brazil, and Argentina. Of course, everyone is welcome to join and to collaborate. And if you are interested, you can email us and we will be happy to talk to you. And as I mentioned, we have been working on a series of events. Particularly, these virtual seminars have been organized since last year. As you can see, Alma Magnetism has a very easy to find YouTube channel. You can subscribe to this channel and get all the information. So we have had 5 seminars. 4 of them have been last year, and we have had one last month by Professor Ivan Schuler. And so let me briefly introduce to you the webinars committee, which, as you can see, reflects the spirit of Alma. We have people from the 6 different nodes collaborating for our common goal. And the coordinator this year is Paula Berkov from Argentina, and the co-coordinator is Felipe Torres. And again, so here are the names in case you're interested in contacting one of the representatives in one of the countries. And of course, you can also email us for any comments or suggestions, which are certainly welcome. So we expect these events to continue, and we have planned a series of seminars for the rest of the year, which we will also announce. And okay, so this is the list. And let me mention that these are planned for the last Friday of the month instead of a Thursday, but we will also let you know. If you're interested, you can also subscribe to our email, and you can receive our newsletter where we give you every detail. And without further ado, I am very pleased to introduce to you our webinar chairperson, Dr. Maria Eugenia Fortes Brolo. Maria Eugenia is one of the people from our committee. She holds a PhD in physics from Universidad Autónoma de Madrid. She currently works as a postdoc at CEPETRO in the State University of Campinas. Her interests are focused on nanotechnology, magnetic materials, and condensed matter physics, in particular in the synthesis and characterization of metal oxide nanoparticles. She works with these materials applied to biomedicine and currently also applied to the oil industry. So now I leave the floor to Maria. Thank you.
Thank you. You can see me? Yes. So just some notice first. By the end of the talk, you can ask some questions. To do so, you can raise your hand. In the bottom, you have reaction bottom. And then you can raise your hand to make the questions. If you cannot raise your hand, you can just turn on your microphone, and then we will allow you to speak. If you're following us through YouTube, then you can also write your question in the YouTube chat, and we will read it to Adriana. So now I will introduce Adriana. Adriana Figueroa completed her PhD in physics at the Instituto de Ciencias Materiales de Aragón in 2012 under the supervision of Professor Juan Bartolomé and Professor Luis Miguel Garcia Vinuesa. During her PhD, she studied systems of magnetic nanoparticles using synchrotron radiation techniques and radiofrequency transverse magnetic susceptibility. In 2013, she was appointed as a postdoc research associate at the Magnetic Spectroscopy group led by Professor Gerrit van der Laan in Diamond Light Source in the UK. In 2017, she was awarded a Juan de la Cierva fellowship to join the physics and engineer of a non-device group of Professor Sergio Valenzuela in the Institut Català de Neurociencia y Nanotecnología. In 2019, she was awarded a Marie Curie individual fellowship where she grows topological insulator thin films by molecular beam epitaxy and complements synchrotron SAS methods with structural and chemical characterization to explore the electronic, spintronic, and magnetic properties of heterostructures incorporating topological insulators and 2D materials. So Adriana, it's a great pleasure. The floor is all yours. You have the word now. Thank you.
Thank you very much, Maria, for such a nice introduction, and thanks to the Alma committee for this invitation and for this opportunity for me to share this. My work is for me it's an honor to be here today. So okay, I'm sharing my screen. Can you confirm that you can see it now, please?
Yes.
Yes, perfect.
Great, thank you very much. So yeah, so as Maria said, I'm a research fellow at the Catalan Institute of Nanoscience and Nanotechnology in Barcelona, and today I'm gonna give you a presentation about the work that we do at the institute. It's about the interfacial phenomena on two kinds of materials, topological insulators and 2D materials, and particularly address and focus on the studies that we do in terms of spintronics. So first of all, I would like to start by introducing the institute that I work on. So ICN2, the Catalan Institute of Nanoscience and Nanotechnology, is located in the outskirts of Barcelona, in the campus of the Universidad Autónoma de Barcelona. So you can see here a map of the campus here, and they were located here. In our campus, we have several labs, several research centers, and one that I want you to focus your attention here is here we have the Spanish synchrotron, which is located 2 kilometers away from our campus, and this is very convenient for us. And today I'm going to show you some results of characterization that we do on our materials in this large-scale facility, the synchrotron radiation source here, which is called Alma, here in Barcelona. So, as Maria mentioned, I work at the Physics and Engineering of Nano Devices group. It's a group led by Professor Sergio Valenzuela, and as I mentioned, I will tell you about a couple of systems that we work on. So our group has two main research lines. So it's the one focused on topological insulator materials, which is mainly the main topic I work on. And in this case, we do epitaxial growth of topological insulators, TIs of this family, which is bismuth, antimony, selenium, and tellurium. And we do a series of characterizations in situ and ex situ. We do device integration, and we do other advanced characterization as in magnetotransport, spin torque fermagnetic resonance, X-ray absorption spectroscopies, angle resolved photoremission spectroscopies, and most recently terahertz spectroscopy. And the other research line that we focus on is 2D materials, including graphene. And in this case, we also work on device fabrication of materials that are exfoliated, and we do stacking to do heat structures of these materials, and we study spin-related transport and thermal electricity on this kind of materials. But so it's not only, I mean, TIs of the these chalcogenide systems and graphene. What we study, we also study 2D materials and other strong spin orbit coupling materials like transition metal dechalcogenides. And in our group, we are interested in the interplay between these kind of materials, and like we do stacking of those, like, because most of them are van der Waals materials. So we are very interested in what happens. I mean, when we interface this kind of materials, and when we create these heterostructures for different devices and different applications. And in particular, we're interested in spin transport and spin manipulation. So we focus in the area of spin orbitronics, and in which we are interested in a series of phenomena like spin Hall effect, spin orbit torque, and so on in this kind of materials. And spin orbitronics is beautifully described as the art of manipulating spins in materials with spin orbit coupling. And what we are interested in is in understanding, control, and manipulation of the spin to charge intake conversion of these materials, and also the interfaces between the stacks that I already mentioned. So, for example, if we take topological insulators and the direct materials, which are the two materials that I mentioned already, we're interested in on what happens with the spin transport of those interfaces of such stacks, of such heterostructures. And for that, we use advanced characterization techniques, and this is what I'm going to talk to you about today. So I'm going to give you a brief introduction and a brief ideas about what we do in terms of advanced characterization of such interfaces in order to be able to control and to study spin to charge interconvention and spintronic, spin transport at such interfaces. So the outline of my talk is the following. I'm going to give you, to tell you about some results that we've got both on topological insulators and 2D materials. So for the TI part, I'm going to show a couple of results. One about spin orbit torques that we have studied at the interface of topological insulators with magnetic materials, and how we can engineer that interface in order to control such torques. And the second part, I'm going to talk about also about TI's interface with magnetic materials, but in this case, it's magnetic insulators, and how we studied proximity effects like those interfaces, and which is also relevant for spintronic applications. And in the second part, I'm going to tell you, I'm going to give you some ideas about how we use an advanced characterization technique also at synchrotron radiation facilities to study spin orbit coupling in graphene interface with transition metal dechalcogenides. In this case, it was about, we use this material, the molybdenum disulfide. So without further ado, I'm going to continue with a first just introduction of what a topological insulator is, a brief introduction about it. So a TI is a material that is characterized electrically, but it's a bulk insulation, but with the existence of topologically protected conducting surface states. So what does it mean? It means that if we look at the band structure of a TI, we will see the bulk band gap here on the states that we see at the band states. But then they are at the same time we have some metallic-like surface states, which are in which the spin momentum is locked and protected by time reversal symmetry. So it's not only that it has some surface states which are metallic or which are metallic-like, but also they have these characteristics in terms of the spin momentum locking, right? And it's this is due. These characteristics are due to the large spin orbit interaction that is that these materials possess. But in terms of electrical properties, let's say without looking at the topology or without looking at these quantum properties, a TI can be seen, or like sometimes it's very naively described as a brick that we wrap in a foil, because it's a brick that is insulating in the bulb and conductive on the surface. But of course, there are more and more features beyond that. Okay, and then in our group, what we do in terms of the TIs is we grow thin films of, as I said, TIs of the family of these chalcogenides. So for that we use molecular beam epitaxy using this machine that I'm showing here in the picture. So this is a very nice machine because we have two chambers to have a controlled growth of the materials. One of those is dedicated to the growth of the TIs. So in this case, we have evaporation cells for these materials of bismuth, antimony, tellurium, and selenium. We have other transition metal here for doping or for growing other systems. And then we have a second chamber, which is dedicated to metal and oxides. And the nice thing is that we can grow samples on both chambers and then connect them and then transfer them in vacuum through this vacuum tunnel that we have here, so that we can grow layers like heterostructures, including TIs and other, for example, magnetic materials or metallic materials here. And at ICN2 in our lab, we also have some important characterization and relevant characterization and processing techniques, like we come with a clean room for nanofabrication and characterization techniques for structural and electronic properties. And then there is another feature that I want to point out here, I want to mention, is that we also have a system to transfer these samples that we grow in this chamber to other growth facilities in our building, for example, to grow by pulse laser deposition, other layers on top or underneath, and then transferring in here. And also we have other characterization techniques like XPS, X-ray photomission spectroscopy, or scanning tunnel microscopy, where we can transfer our samples grown here to those characterization techniques without breaking vacuum, using this USB suitcase transfer system. All right, so what are the characteristics of these TIs that we grow by MBE? So we in our group, the growth of high quality thin films of these materials, these bismuth, antimony, tellurium, and selenium TIs, have been established and optimized. So we grow. These materials are what we call like van der Waals materials because they grow layered in a layered feature, and then they are characterized by this basic unit, which is what we call the quintuple layer. And each quintuple layer, which is formed by 5 layers of 3 of them of the chalcogen atom, and then 2 of them by bismuth of antimony. These are linked or like bonded to the other basic unit, to the other quintuple layer, by van der Waals forces. So we end up with a layer system or van der Waals system. And we have optimized the growth of these TIs on barium fluoride, which is the substrate that we use in this case. And then it has been established how to, what are the conditions to suppress the appearance of in how to avoid these twins in the system, so that we end up with a smooth surface on top of these TIs. And why is this relevant? This is relevant for studying and for taking advantage of the transport of the electronic transport properties in these TI systems, in these films. So it has been also established how to tune the location of the Fermi energy within the gap of these materials. For example, for this alloy, which is what we call BST, bismuth antimony telluride. And then we've seen that the position of the Fermi energy, it depends, or it depends on the concentration of antimony in the material. And this is relevant because with that control, we are able to suppress the contribution of bulk carriers for the electronic transport. What does it mean? So in these materials, we have a combination, as I said, of bulk transport and the surface states. But ideally, in an ideal TI, we want to to make sure that the most relevant, or the one that contributes the most to the electronic transport in these materials, are the surface states that so that we can use them for different applications, in particular for spintronic applications. And with that, we've seen that in this alloy, we obtained that we were able to get such conditions around 60% of antimony, right? And then once we've established what are the optimal conditions for this BST material to use in transport measurements, we now can continue to incorporate this into heterostructures with magnetic materials, because we are interested, as I said, in exploring the spintronic properties. So one first study that I'm going to show you today is about studies of spintronics in TIs, in particularly about a spin orbit torque at interfaces of the TIs to ferromagnetic materials. In this case, the ferromagnetic material that we used was permalloy. So the permalloy is an alloy between iron of iron and nickel. And then when we grow these samples of BST, or the TI BST with the PI, we're interested in understanding, or in studying what are the what happens at this interface in terms of the spin transport that we can have in this material, in this stack. And for that, we use this technique that is called spin torque fermagnetic resonance, which is a current-induced fermagnetic resonance. So where we pass a current through this stack, the current flows through these materials, and then because of significant non-equilibrium spin density at the boundary of this interface between the TI and the permalloy, we are able to have such spin accumulation at the interface that creates a torque and can modify the magnetization dynamics of that magnetization vector on the TI. So we are able to modify such magnetization dynamics on the permalloy, and even to reverse the magnetization of that permalloy. So we are interested also in performing a magnetic switching in these stacks. And then with STFMR, when we analyze the dynamics of that magnetization, we observe that using the LLG equation, we can identify different contributions to those dynamics. And then if we will have, of course, this is the FMR signal that we see, and then we have a component that is symmetric and a component that is antisymmetric. And the symmetric component is what we call the damping or anti-damping. And the antisymmetric component will have two different contributions as well. One that we call, that is the torque. We have a diagram here. One is the Ørsted-like torque, and the other one is the field-like torque. And the Ørsted-like torque is simply because we have a current passing through the sample. And the field-like torque is the one that we're interested in, because that is the one that we are interested in. Like, we want that to be more relevant in our sample, because that would be because of these effects of the Rashba-Haldestan effects at the interface. And that those are as a consequence of the spin structure at the interface of the TI. But what happens is that when it's well known, it's well established that when you have such interfaces of the TI with a permalloy, or with a ferromagnetic layer, you usually have interdiffusion, or like these interfaces are not perfect. So what we did was to study with we performed this spin orbit torque analysis, this spin orbit torque study for different spacers between the TI and the permalloy. So we used tellurium, silver, and aluminum, and then we saw that depending on the kind of spacer and also depending on the thickness of that spacer, we can control which contribution is more relevant in terms of the field-like torque or the Oersted-like torque. And we observed that the most efficient spin orbit torque is obtained at the interface with aluminum. I mean, when we use an interlayer of aluminum in between the topological insulator and the permalloy, and this is correlated to what it's. What we use another characterization technique, which is X-ray photoremission spectroscopy, in order to study what happens at that interface, or what's going on the interface, and then we see that we're able to correlate that appearance, that contribution, mostly contribution from the field-like torque, with the improved, because with the aluminum, with the improvement of the interface when we use that spacer of aluminum. And that happens mostly with aluminum and also with tellurium, but tellurium is not a good material to use with in spintronic applications in this case, because tellurium is a very good spin absorber, and we don't want the tellurium to absorb all the spins that are accumulated on the TI. We want those spins to go through the permalloy and then exert a torque on the permalloy, and do some switching of the magnetization and so on. So in that case, we observe that the optimum material to be used here is aluminum of about 6 nanometers. So this is the best, the optimized result that we got. And then another study that we want to use with this kind of materials is to explore, to use this kind of stacks to use in applications of terahertz emissions. So to design emitters in the terahertz range that can be based on these optimal spintronic properties of the TI based devices for optimal, efficient emission of terahertz. So there's already some works that use heterostructures of TIs interface with other magnetic materials like cobalt, where they have observed that indeed, if we use this kind of materials for these terahertz spectroscopy studies, there is an enhanced terahertz emission of these kind of stacks. And we want to, this is a project that we're working on at the moment, where we are using these kind of stacks that we already optimized using the interlayer of aluminum in between the TI and the permalloy to explore such emission of terahertz in these kind of stacks. Another system, other system, as I said, we not only use these TIs in proximity or in interface to permalloy or to metallic materials, but also to non-metallic materials like what we call magnetic insulators. And this is relevant because we are interested in a study proximity effects at the interfaces of these TIs with magnetic materials. So, and why is that? Because we know, it's interesting to study that the TIs are there are some effects and some interesting novel phenomena that arises in the interfaces of the TIs when we introduce magnetism when we induce or when we make these TIs magnetic, and in order to break the time reversal symmetry in the system. For example, one relevant phenomena that comes up into play is the quantum anomalous Hall effect. And in order to observe this kind of novel phenomena and to break time reversal symmetry in the system, we can either dope the material with magnetic impurities or to use proximity with ferromagnetic layers. And in this case, as I said, is best to use magnetic insulator in order to avoid the interference between those surface states with the metallic character of the magnetic material. So here, for example, I'm showing some materials that you can use. So you can use European sulfide or rare garnets or other novel materials that are being explored, like ferrites or these materials of bismuth tellurides or antimony telluride using transition metals like manganese. So I'm going to tell you, to show you some results about what we've done, what we've used to study proximity effects with the TIs with European sulfide. The first material that was used and what has been studied very, very widely is this European sulfide. And then there have been several reports about the properties, not only transport properties, but also properties of these interfaces of the topological insulators with European sulfide. And then they have observed very, very interesting phenomena. In particular, they have observed like unusual magnetism in these interfaces. For example, they have observed ferromagnetism at room temperature, even though the European sulfide is magnetic down only up to 15 Kelvin, in principle, but they have been able to, or like they report ferromagnetism at room temperature. Also, the anisotropy of the stack, they say that it's favorable, an out of plane anisotropy orientation in this stack instead of the in-plane that is usual for the bare European sulfide. And also, but the most relevant result that has been observed is that they report an enhanced magnetic signal within the TI. Even though the TI is not magnetic, they claim that there is a magnetic signal within the TI. So we wanted to explore these to study these phenomena. And in this case, we used a very, very relevant advanced characterization technique that allows us to have magnetic sensitivity in a very, very selective way, which is what we call X-ray magnetic circular dichroism. So this is a technique that is performed at synchrotron radiation facilities and is based on the transitions from, it's based on X-ray absorption spectroscopy and the transitions from core level, from the core level to the core level electrons to the continuum. And then what allows us to, it provides very relevant information about element, shell, and layer selective magnetometry. And it's also, because it's based on a spin-dependent absorption of the circularly polarized photon that we shine this sample with. And then with this technique, we are able to obtain, we focus the energy to the magnetic elements in a material, and not only to the magnetic elements, let's say, for example, in this case, for the TI, we are interested in looking not only at the magnetism of the European elements in the European sulfide, but also on the magnetism on the non-magnetic elements. So because of these claims of the induced magnetism that has been reported in the bismuth and the bismuth selenide or bismuth telluride topological insulators. So the key questions that we wanted to answer with these was to look whether there was an enhancement of the European magnetism on these interfaces, also about the anisotropy, whether there was an out-of-plane orientation of the European moments, and whether there was an enhancement of the Curie temperature of the system as reported. And the most relevant result that we wanted to confirm or like to look for was whether there was an induced magnetism within the TI. So for that, we grew our stacks. So we grew our topological insulators of this family with a series of samples of bismuth selenide, bismuth telluride, bismuth antimony telluride, and antimony telluride. We characterize them in situ and ex situ with a series of characterization techniques to demonstrate that there was epitaxial growth with no additional phases, and with good quality of the interfaces between the TI and the europium sulfide. And then we took these samples to the synchrotron, and then we measured XMCD. So the first results that I'm showing here is the ones at the europium energies. So we demonstrated here, we observed that the europium atoms in these materials, in all these stacks, are mainly 2+. I mean, the valence is 2+, which is the one that is for ferromagnetic europium. And we observed that there is no enhancement of the europium, I mean, by application of the magneto-optical Stern rules of these signals, of the XMCD signals that we observed on the europium atoms. We obtained the values for the magnetic moment for the different samples, and we compared with a reference sample of single europium sulfide. And then we don't see any, much difference between what we observe for these samples interface with the TI and the reference samples. There's no enhancement of the europium magnetic moment. And also in terms of the anisotropy, we observed, we studied at different geometries to see the components in plane and out of plane for the europium sulfide. And then we observe that in all cases, all samples have an in-plane easy access of magnetization. Not only with XMCD, but also with regular squid magnetometry, for macroscopic squid magnetometry. And then in terms of the enhancement of the Curie temperature that was claimed, because of the interface with the TI, there was an enhancement of the Curie temperature that indicates that they claim that they observe ferromagnetism at room temperature. Well, we don't see that. We measure both in squid magnetometry and with XMCD hysteresis loops, and we observe that at 5 Kelvin, these layers are ferromagnetic, and then they are paramagnetic at 20 Kelvin already. And then this is, it matches well it agrees well with the Curie temperature observed for single layers of europium sulfide. So no changes on the Curie temperature because of the interface with the TI. And now the main result is whether to demonstrate whether there was an induced magnetic moment on the non-magnetic atoms of the TI. So we focus the energy, we tune the energy to the non-magnetic atoms, so bismuth, antimony, tellurium, and selenium, which are the atoms of the topological insulator layer. And then we try to measure XMCD on those systems, but we didn't see anything. So there is no evident XMCD signal above the noise level for the data measured. But by application of the Stern rules here, we are able to establish what would be the upper limit for the induced moment in these signals that we measure. We see that the spin moment that we would see would be below 10⁻³ Bohr magneton. And this is in stark contrast to what has been reported, for example, by other studies in polarized neutron reflectivity measurements for these kind of systems of TIs with europium sulfide, where they claim, they report magnetic moments up to 1 Bohr magneton that we do not see. And then what we demonstrate is that indeed this is not, we don't have proximity effects. We don't have induced moments on the TIs. All right, and then we do also this not only for the europium sulfide. Our next study was to use other kind of magnetic insulators, those that have, for example, higher Curie temperatures. For example, YIG, which is yttrium iron garnet, or thulium iron garnet. So these rarer iron garnets have been also studied in interfaces in heterostructures with topological insulators in search of these proximity effects. And then in magnetotransport measurements, it has been reported that indeed there have been, I mean, they are observed some spin polarized features at the interfaces of those magnetic insulators with the TI. And then, so what we decided to do was to grow this kind of material, this kind of heterostructures as well, to do XMCD. So in that case, we grew the iron garnets by pulse laser deposition in a different chamber, not on this chamber that I showed already. And we grew it on a PLD system, also at ICN2 in our facilities. And then we transported those samples to our MB system to grow the topological insulator on top. And then we end up with these stacks that I'm showing here. And then we characterize them before we do XMCD measurement. So just to show you that we also have epitaxial growth of these materials. I mean, here I'm just showing the results of the growth for YIG, for the yttrium iron garnet on the substrates. We perform some pre-treatment of the substrates in order to have very good quality of the yttrium iron of the garnets. And for the thulium iron garnet, we collaborate with people in ETH Zurich who provide these films of the thulium iron garnet. So we have these two kind of systems, and then we grow the TIs on top. And in this case, for the growth of the topological insulators on our MBE machine, we perform a two-step growth, which means that we grow first a buffer layer, or like a seed layer, at low temperatures, and then we anneal to the growth temperatures, and then we continue with the growth, and then we end up with very nice layers at the end of the growth. And then for these, I mean, we grow these stacks, and then we take them to the synchrotron to perform XMCD. So here I'm showing results of the iron energies of the iron edges performed on both YIG interface with bismuth selenide, and in this case of thulium iron garnet, TIG, what we call TIG, on BST. And then I'm showing here that we have a very strong XMCD signal on the iron atoms for all samples, all with the field applied perpendicular to the sample plane, which is what we are interested in also, to measure for the orientation perpendicular to the sample plane. And then, the next thing that we did was to tune the energy to the non-magnetic atoms again. And then in this case, we also observed no XMCD signal on these atoms from the TI. So here I'm showing, for example, for selenium, what we saw for selenium on the YIG interface with bismuth selenide. And then we see that the XMCD in this case is below 0.5%. And then at the tellurium edges for the TIG interface with BST, we see that the XMCD is below 1%. So in this case, again, I mean, we have similar results to what we observed for the bismuth selenide interface with the European sulfide. So no induced XMCD, no proximity effects of these in this case. But this is in stark contrast to what has been reported. I mean, in transport measurements. So here I'm showing results of a recent paper. In this study, they do both transport measurements when they see some features of proximity effects, in the sense that they observe anomalous Hall effect on these stacks, which should be resulting from these, which will result from these proximity effects. In this case, is bismuth telluride interface on YIG, and they also do XMCD in this case. And then they also saw that there's no XMCD on the tellurium atoms, for example, for this kind of systems of bismuth telluride interface with YIG or with interface with TIG. and just as what we do, but they do see some induced or like some proximity effects in transport measurements. So there is an incompatibility here in the sense of like how can we reconcile these two results? So it's important to know what happens here. So what they do, I'm sorry. So it's important to understand. So this is still work in progress in order to see why can't we observe such results, or why can't we why these results are not reflected on XMCD, or where are these results coming from then? Okay, all right. And with this, I finished the first part of my talk, which was about topological insulators interface with different kind of ferromagnetic materials. I just want to quickly give you some take-home messages on this part. Just important to let you know that in the case of TIs interface with permalloys, intermixing plays a critical role in the generation of spin orbit torques, and then these properties of the topological insulators are largely improved when we place an interlayer, and also it because of the position of because of the introduction of such interlayer, we can also have a strong variation in the nature of the spin orbit torque, so that we can have an enhancement of the field-like torque at the interface, which is important and relevant for applications, for spintronic applications. And then I also show you how some results of XMCD on these TIs interface with magnetic insulators. In the two kinds of insulators that I used were europium sulfide and yttrium iron garnet. And then I show you that there was no clear signal or XMCD signal on the non-magnetic atoms of the TIs in contact with the magnetic insulators. And this is in stark contrast to what has been reported for transport measurements and other characterization techniques for such heater structures. And it's important to know, like, I mean, there is still some open questions, because we need to know how to reconcile this observation of a magnetic exchange, I mean, with the observation of a magnetic exchange gap. So one idea, or like some hypothesis, is that XMCD might not be sensitive enough to such a small band gap that is generated at this material. So that could be an idea, but there is still work in progress, and there is still open questions to be answered. With that, I finished my first part, and I'm going to move to the second part, which is very briefly, just going to show you some results on 2D materials using, some studies that I've performed of these 2D materials also with advanced characterization techniques using synchrotron radiation techniques. So in 2D materials, let's say the material for excellence is graphene. And graphene is being used for spin transport, for spintronic, let's say for spintronic studies, because it's a low spin orbit. It's a low spin orbit coupling system, where the spins can flow with the very long distances, and it's very interesting to be used in devices for spintronic applications because of that properties of the spin transport. However, also because of the low spin orbit interaction, you have no control of such a spin current. But the properties in graphene can be tailored, for example, by interfaces, by proximity with other materials that have, for example, high spin orbit coupling. And in this case, we use transition metallic chalcogenides, which are materials that have this formula, where the transition metal can be tungsten, molybdenum, for example, and then the chalcogen atoms is sulfur, selenium, tellurium, and then we have, the nice thing about these TMDCs that we call is that they are also van der Waals systems, and then we can exfoliate them and then create stacks as we wish. So we can put the graphene on top of the TMDC, or the TMDC transfer on top of the graphene, and also to do sandwiches. And I mean, they're very versatile systems to do stacks and to study spin transport. So in our group, these interfaces between the TMDC and the graphene materials have been studied also by spin transport experiments, in order to explore what happens. I mean, this proximity-induced spin-orbit coupling in graphene. So what has been observed is that if you transfer a TMDC material on top of graphene, and then you study the spin transport in this system, you have an isotropic spinionization in graphene as a result of proximity to the TMDC. So if you study the spin transport with one orientation of the magnetic field, and then with the perpendicular orientation of the magnetic field, you see different response, different results for the transport of that spin current. And then that is a result of as a consequence of the spin-orbit coupling induced in graphene as a consequence of because of the interface with a TMDC, with a large spin-orbit coupling material. And okay, and in this case, this is also relevant for spin-to-charge interconversion at that interface, because these are also results by people in our group, where they had been observed tunable spin Hall effects and spin galvanic effect contributions that you can have at the interface of these systems, which is very relevant for spintronic applications, where you can have control of the spin to charge interconversion at those interfaces. So, but these kind of measurements of proximity-induced spin-orbit coupling in graphene are somewhat not a direct measurement of the spin-orbit coupling induced in induction in the graphene. But we wanted to explore other ways, other characterization techniques, other techniques to study such spin-orbit coupling. And for that, we are using X-ray absorption spectroscopy at synchrotron radiation facilities. So again, as I told you, we use, it's the same technique that we use for XMCD, but in this case, we don't apply a magnetic field. We just study the X-ray absorption of the materials. For example, in this case, we study the X-ray absorption of the molybdenum in a molybdenum disulfide material interface with graphene. And then this is because there is a rule, a Zoom rule, that it has been established for this XAS, for this X-ray absorption spectroscopy, that correlates the spin-orbit coupling in the material with the intensity that we observe on this X-ray absorption. So the Zoom rule for isotropic XAS tells us that this branching ratio that we define as the ratio between the intensity of the intensity between these two transitions, the L2 and the L3, is proportional to the angular part of the spin-orbit interaction. So that if we measure this on these materials, XAS gives a direct measurement of the spin-orbit interaction. So that's what we did. So we took our samples. So what are the samples that we took? So we have a graphene with interface with MOS2. So it has been done, this is in collaboration with people in IMEC in Belgium, is that they grow on separately graphene using chemical vapor deposition, and then they grow on a separate, they grow also samples of MOS2 also by chemical vapor deposition. And then they transfer one on top of the other using what they call a dry transfer method. And then we end up with a stack of MOS2 with a graphene on top. And then we have single layer MOS2 with single layer graphene on top. And these are like images of this kind of stacks that we've got, use images of with AFM. So now that we have these stacks, we take them to the to the synchrotron to measure X-ray absorption spectroscopy. And then the first thing that we did was to measure X-ray XAS at the carbon edge, just to characterize the graphene and to see how these how the spectra look like for the graphene without MOS2 and graphene with MOS2. And then what we also did was, in order to study these orbitals and in graphene, we use XAS with linear polarization, because depending on the polarization of the light and the geometry that we perform the measurements, we can study these we can probe the different orbitals in graphene. So for example, if we use this geometry, we probe only the orbitals that are in plane, which are the pi orbitals. And then if we use a different geometry, we can also explore the sigma orbitals. And then we compare the results that we observe for the two kind of stacks. The graphene without the MOS2 and the graphene with MOS2. And we observe changes in the spectra that are relevant and that are signatures of hybridization, which means orbital mixing between the graphene and the MOS2. And then also, if we tune the energy to the sulfur KH in the MOS2, with and without graphene, we see changes that are also observed at the sulfur electronic states, and then that are also, that they agree with those results of hybridization. And this is also something that has been reported by measurements of angle result photoemission spectroscopy, when they have observed hybridization of these orbitals in graphene as a result of the proximity to MOS2. And then finally, we also measured at the molybdenum edges, at the molybdenum energies, in order to study that, to explore, to study, to extract the values of the branching ratio in the system, in the MOS2 graphene system, compared to the to the system without graphene. And then we observed that indeed there is a reduction in the branching ratio on the stack of the MOS2 graphene. So it means is that we have changes in the spin orbit interaction at the stack compared without the MOS2, without the graphene, which means that there is indeed induction of, there is a probe of a spin orbit interaction, and then at the interface of MOS2 and graphene, there is indeed some effects that are relevant or that are observed in this kind of systems of this stack. So just to conclude this part, I just want to tell you that spin orbit interaction, we've used X-ray absorption spectroscopy. We observe very clean spectra for single layer graphene and single layer MOS2. We observe signatures of hybridization between the pi orbitals in graphene and the 3D orbitals, not 3D, the T orbitals on MOS2, the 4D orbitals on MOS2, and then that there is a spin orbit interaction can be intrinsic in graphene through proximity effects, and those are reflected on the XAS, because I observed that we see changes in the branching ratio of the molybdenum, and they're also evident in changes in the carbon KH. And with this, I finish my presentation. I want to thank all our collaborators. Not only people from my group and ICN2, but also our collaborators in different synchrotron radiation and also in other labs. I also want to acknowledge funding from different funding bodies. And I want to thank you very much for your attention.
Thank you, Adriana. I have to say it was a lovely talk. I really enjoyed your talk today, and I have to say it's a really nice slides, really clear presentation. Yes.
Thank you very much.
So now you can raise your hand, and again, the raise hand feature is in the bottom of your screen at the reaction button. you can click there, and then there's the raise your hand feature. You can do so, and if for any reason you cannot access to this feature, you can just open your microphone and you can ask your question. And if you're following us through the YouTube, you can write your questions here in the chat so we can read to Adriana. So let me see if there is someone with the raised hand. Rafael, yes, you can open your mic.
Thank you so much, Adriana, for the talk. Really nice talk.
Thank you.
And I have a question about the first part of the talk in the spin orbit torque effect. And you say that the source of this effect is the spin galvanic effect, but usually you could have contribution of the spin Hall effect also. I would like to know how do you distinguish?
Well, it's not easy, but yeah, you can demonstrate by the features that you observe and the torques that indeed you can have I mean, this is one of the typical questions that we had. I mean, also for the referees, because it's a typical question. But yeah, depending on the features that you see on the analysis that we perform for the line shapes of the FMR signals that we got, we were able to distinguish those. So indeed, we managed to demonstrate that it was not as a result of a spin Hall effect.
Thank you so much, Adriana.
Juan Gabriel, I know that you cannot raise your hand, so you can open your mic and.
Yeah, okay. I thought I could, but yeah, I just found out that I cannot. Thank you, Adriana. That's a very nice talk. I have a lot of questions, but I only wanna ask a couple. So regarding the FMR measurements, can you comment on how do you perform the measurements? Are they done in cavities or is a broadband setup?
It's a broadband setup, but in this, I mean, it's similar to a broadband setup, but this is what we call a spin torque FMR. So you apply a current through the sample. I mean, it's you have a coplanar waveguide patterned on the sample, and then you apply a AC current at the same time as you perform you use a signal generator to perform these measurements. So yeah, it's broadband. Yeah, but it's broadband in the sense that you use you can use a vector network analyzer for that.
So you have a coplanar waveguide, and you send it. What is the frequency that you use for this?
We go up to 20 gigahertz, I think. Yeah.
Okay.
So you can apply different frequencies. I mean, as in broadband. I mean, that's why it's not a cavity, so you can apply on the coplanar waveguide, and then we use lock-in detection for that.
I see. Okay. So is there any, because I don't remember seeing any frequency dependent measurements. Is that something you do?
Yeah, we do that. But I didn't show it. It's on the pipe there, so you can take a look at the. I mean, the details are here in this paper. So yeah, we have, of course, frequency dependent measurements, and yeah, because I mean, for the analysis, we do that too.
Exactly, because that way, you know. So in the LG equation that you show at the beginning, so you have this extra term that I haven't seen before, but I don't follow much this. So this extra term is the field like, exactly. So is this, can you comment on the origin of, I mean, it's phenomenological, of course, but I mean.
Yeah, this is what is also related to what Rafael was asking about. So here, I mean, the Ørsted-like torque is the one that is just due to a current flowing through the sample, and then the field-like torque is the one that you have that is here, as you said, is perpendicular to the. It's also perpendicular to the sample here. I mean, to the magnetization here. So you have this two kind of contributions that that are part of the antisymmetric component of the FMR. And so this is the one that we're interested in, because this is the one like related to the spin accumulation at the interface here.
I see. Okay. And since you have to make this coplanar, I mean, this setup that to measure the FMR. So do you use any capping layer for the top? I'm just curious about.
A capping layer, yes. We use aluminum, and then it oxidizes inner. So it's what we call aluminum oxide, but we don't evaporate that aluminum oxide. We evaporate aluminum and then we allow it to oxidize. Yeah.
Because I know that introducing those capping layers also, they shift the resonance field somehow. I don't know if you test this before.
Yeah,
so I'm curious about how do you differentiate the both effects, because that's not usually done.
Yeah, that's true. But because actually the capping layer also, I mean, we observed effects here, for example, in XPX, in X-ray photoremission spectroscopy. Just by having the capping layer, you can have that effect of shifting of the position of peaks in spectroscopy, but then it's not as I mean, since all of them had the capping layer, and we were interested in studying the effect of the interlayer and in between this stack. We kept that capping layer fixed. And then we studied like the effects of the interface for different thicknesses of the interfaces. So, I mean, by fixing the capping layer, we knew that it was. I mean, especially on top of the TI, but also, I mean, have in mind that the TI the capping layer in this case is on top of the ferromagnet, right? So it's not affecting the part of the TI.
Yeah, okay. Thank you, Adriana.
Thank you.
Okay, we have a question from Natalia Cortez in YouTube. She asks, have you analyzed the edge effects or the edge states of MOS2 or graphene in the proximatized structure?
Well, I haven't, but my colleagues are doing so. So yeah, I mean, it's part of the project of other colleagues who are working on to do transport measurements in electronic transport, and also to do some electronic structure, say for example with ARPES or with other advanced characterization techniques. So I don't have the results yet. Or we don't have the results yet, but it's some work in progress that is being done in our group. Thank you for the question.
Okay, someone else? Okay, Isabel, you can open your mic.
Hi, Adriana. Could you hear me?
Yes, I can hear you. Thank you.
Thank you very much for your talk. Bueno, I have a couple of questions. One, regarding this interdiffusion of any metal that you have in contact with the TI, how do you consider that for the quantification of the spin orbit torque efficiency? I mean, you consider that is just on this topological insulator or this new interdiffusion layer with selenium and tellurium?
Yeah. So as you say, there is. And also it has been reported there is interdiffusion, and this is what we wanted to explore. So it's what we do is in fact to make sure. To take into account that it's. You take into account that let's say that layer here, that is in this case, for example, is is reported to be 3 nanometers. But then when you use different kind of interfaces, you are reducing such interface. Such intermixing layer or interfacial layer. So yeah, you take into account that. we made an estimation of that.
Yeah, it's more like an value. Because we will have different spin diffusion lengths because there are different materials and the values.
Yeah, but unfortunately we didn't have clear TM images, like to say, okay, at this part and in this kind of system or with this interface we have this thickness or so on. Unfortunately not, so we made an estimate.
And you have to know the resistivity for each layer too, so it will be more tricky to have
it's not easy, but yeah, we did some estimation.
Yeah, okay. Well, I am working with BS too, and it's kind of
with which material?
bismuth selenide.
Okay, with bismuth selenide. Okay.
But in non-local configuration. Well,
right.
Well, another question for the 2D. You work back in the CVD, no? Have you tried with exfoliation, graphene and exfoliated in MOS2 or?
I haven't tried. I mean, for these stacks that I showed, we haven't done. At the beginning we had some samples that we wanted to try, but since we got these good materials with CVD, I mean, they are very good. They had good quality, so at the end we took these samples. We didn't try with the exfoliation and transfer, say, from crystals and so on. And also here you have a very nice control, and then also here with CVD, what you manage is to have a large covering area of both graphene and MOS2, and this is what we want for this kind of measurements, because that way we gain in signal. Because for the exfoliated materials, you usually have very tiny flakes that you have to look for, and it's not that easy for these kind of techniques. But I mean, we could try to do a mapping, but it's not that straightforward. That's why we went for CVD grown materials.
Maria. Thank you, Adriana.
Thank you.
Anyone else have some questions? If not, I have a curiosity.
Yes.
How complex is the TI synthesis that you showed in the beginning? How fast it is? How is the
well, it's since it is MBE, it's a slow process to grow. But it's very nicely controlled. So it's very similar to growth of semiconducting materials like gallium arsenide or so on. So it's because these materials are also like the element 5 materials and so on. So it has been established, very nice protocol. So it's, I mean, if you manage to have a good MB system to control the temperature of the growth, I mean, to control the temperature not only of the cells but also of the substrate, which is what you usually have. And I think it's a nice system to do, and then you manage to get very, very nice and controlled growth of the layers. So yeah, it's good.
Thank you. Let me see if you have any more raised hands here. I'll check. So far we have no more questions.
Okay.
So I would like to thank you again for your time and for accepting the invitation. Thank you very much. It was really lovely.
Thank you very much for the invitation again. It was a pleasure to me and an honor to share this in this space. I mean, our results in this space. So thank you.
Thank you. And if anyone wants to make part of the Alma Association, you can email us or send a message or to any of us. And thank you again. Thank you all for being present here.
Thank you. Thank you very much.
Thank you.
Thank you. Bye.
We can, yeah, maybe an applause will be